Hello everyone. This video will cover notes for section 2.1. We'll begin by addressing the output question. We're asked to find the output of the following: f of -3, g of -3, h of -3, and m of -3. So each of these four functions, we will substitute the value of x, which is -3, to determine what the function would be after we substitute that x coordinate. So in our f function, for the first example, we're going to substitute -3 where x, everywhere we see x. And that will become f of -3 equals -2x, but we're substituting -3 for x. So we'll put the -3 in parentheses, plus 3 at the end. And then we want to continue to simplify. -2 times -3 gives us +6. Plus 3, so the value of the function when x is -3 would be 9. Now finding g of -3, we're going to substitute -3 everywhere we see x using the g function. In the g function, we have 5x squared minus x. So g of -3 would equal 5 times -3, that's -3 to the second power, minus -3. Notice we place the x in parentheses, substituting -3. Now let's simplify. -3 squared will give us +9. Carry down the 5 that's in front of the parentheses. Now minus -3, that becomes +3. 5 times 9, and we'll get 48 as the value of the function when x is -3. Now let's find h of -3 using our h function. H of -3 equals the absolute value. These two vertical lines mean absolute value. The absolute value of -3 minus 7. -3 minus 7 is -10. And we want to find the absolute value of -10. The absolute value means the distance from 0 on the number line. So this will be 10. -10 is 10 spaces away from 0 on the number line. So the value of the h function when x is -3 will be 10. Now m of -3, we're substituting into the m function. We'll have m of -3 equals 3. There's no x coordinate to the right of the equal sign. This is what's called a constant function. No matter what number you substitute for x, you're going to get the value of that function to be 3. Next example, we want to write a formula for the function c, which computes the circumference. So c stands for circumference, with a circle, or of a circle, with the radius of length r. So when we see the letter C, we're representing circumference. And when we see the number given, that length represents the radius in feet. So in this case, we're given C of 10. We're finding C of 10, and the 10 represents the radius. So R equals 10. Give an exact answer. When we're asked to give an exact answer, that means that we want to keep the pi symbol. We don't want to substitute the estimation of 3.14. We want to keep the pi symbol. Now, what are we keeping the pi symbol for? We have to remember the formula to find circumference, and there are two forms we could use. One would be multiplying 2 times pi times radius, or we could multiply pi times the diameter. So D stands for diameter, R stands for radius. Now both of these formulas calculate the circumference of a circle. Because we're dealing with the radius, we're going to use the first formula. So we're going to calculate the circumference using our circumference formula. C equals 2 pi r. So we need to multiply these terms together based on the information we're given. So we're given the radius of 10, r equals 10, so we're going to substitute 10 for r. Regarding the pi, we're going to keep the pi symbol exactly like we see it. So 2 times pi, we're keeping the pi symbol, times the radius is 10. Simplify a little bit more, 2 times 10 gives us 20 pi, and carry down the pi. So this will be our circumference, given an exact answer when the radius is 10, the value of that function when the radius is 10. Now, we're asked to find C of 10, so we're looking for the radius again. We're looking for the circumference again, but when the radius is 10. But this time we're asked to round to the nearest tenth. This time we don't want to keep the pi symbol. We have to use our estimate. We're going to substitute 3.14 for pi. So using our same formula, C equals 2 pi r, we're going to substitute. We have 2, and then for pi, we're substituting 3.14. And then our radius is 10. So we're going to multiply these three terms together. 2 times 3.14 times 10, and we're rounding to the nearest tenth. You should get 62.8 62.8 feet. Now the rest of the question says interpret the results in words. What does the 62.8 feet mean? It means that a radius of 10 for some circle, right? The circumference of that circle when the radius is 10 is going to be 62.8 feet. So the circumference of a circle with a radius of 10 circumference of a circle with radius 10 is 62.8 feet. This is how we would interpret the results in words. Now let's look at the next example. We're asked to sketch the function f of x equals 3x minus 5 by plotting points. And we aren't given values for these points here. Therefore, we're going to create a table and find our own points. We're going to create a table with the x and y coordinates. And we're going to substitute two values for x. Whenever you see a function that's written in slope-intercept form, y equals mx plus b. We say this is written in slope-intercept form because f of x is the same thing as y. And it's by itself. On the left side of the equation, we have some number times x on the right, and then we're adding or subtracting the y-intercept. So when you have a standard linear equation written in slope-intercept form, you only need 2 points to graph the line. So we're going to use easy points. We're substituting 0 for x and 1 for x. We're going to substitute those values into our function and determine the values of y. We'll plot those 2 points we get and then connect them to draw the graph. So let's find the value of the function when x is 0. So f of 0 equals, we have 3x minus 5, but everywhere x is, we're substituting 0. So 3 times 0 minus 5. 3 times 0 is 0. And 0 minus 5 gives us negative 5. So the value of the function when x is 0, our y coordinate also will be negative 5. Now let's find f of 1. So f of 1 equals 3 times 1 minus 5. 3 times 1 gives us 3, minus the 5 becomes negative 2. So the value of the function when x is 1 would be negative 2. Now we have our 2 ordered pairs. We can plot them and create our graph. So 0, negative 5, that's 0 on the x-axis down to negative 5, 1, 2, 3, 4. 1, 2, 3, 4, 5 on the y-axis. Let's go ahead and label this point as 0, negative 5. Our second ordered pair is 1, negative 2. So 1 on the x-axis down to negative 2 on the y-axis. 1, negative 2. And we'll connect these 2 points to create the graph. Why is f of x called a linear function? Linear, just like it sounds. This is a linear function because the graph creates a line. Because the graph is a line. All right, let's look at the next example. We'll notice immediately that our function is a little different than the previous example. Now, because of that, we want to graph it in a different way. We're going to need a few more points in order to see how this graph will look. So we're going to substitute more than 2 points into this given a function. So instead of just 0 and 1, we're also going to plot 2 for the x coordinate, negative 1 and negative 2. The reason we're substituting more values is because our power of x has increased. So we need to see what's going to happen on both sides of the y-axis when we plot our points. So let's go ahead and find the value of these functions when x is 0, 1, 2, -1, and -2. So the value of the function when x is 0, we'll start there. We plug in 0 where x is. And we'll right over here to find f of 0. We're substituting on the right side of the equal sign. We'll have -0 to the second power plus 4. And 0 to the second power, that's just 0. And 0 does not have a sign. So -0 is the same thing as 0. And then we're adding 4. So 0 plus 4 will be 4. The value of the function when x is 0, the y-coordinate will replace as 4. Now let's find f of 1. We'll have f of 1 equals -1 to the second power plus 4. 1 to the second power is 1. However, look at that minus sign that's in front of the parentheses. We want to carry it down. We have to apply it this sign. Plus 4 behind the parentheses. -1 plus 4 gives us 3. So the value of the function when x is 1, our y-coordinate will be 3. Now f of 2. So f of 2 equals -2 to the second power plus 4. And 2 to the second power is 4. We'll carry down the minus that's in front of the parentheses. Plus 4 behind. -4 plus 4 is 0. So the value of the function when x is 2, this is a 2, we get 0 for the y-coordinate. Now let's find f. Let's move up here. Let's find f of -1. F of -1 would be negative, and then in parentheses, -1 to the second power plus 4. -1 to the second power is 1. We'll carry down the 1 in front, and -1 plus 4 is 3. So the value of this function when x is -1, we'll get 3 for the y-coordinate. And now lastly, f of -2. We have negative, and then -2 in parentheses to the second power plus 4. -2 to the second power is 4. Carry down the minus sign. -4 plus 4 gives us 0. So the value of this function when x is -2, we get 0. Now let's plot these points. 0, 4, 0, and then up to 1, 2, 3, 4 on the y-axis. 1, 3, 1, 1, 2, 3 on the y-axis, and 2, 0. The 1, 2, 0 will be right here on the x-axis. -1, 3, we're going to move over to -1, and then up to 3, 1, 2, 3, -1, 3, and -2, 0, 1, 2, -2, right here on the x-axis again. Now immediately we see that our points don't make a straight line. Now because when we connect these points, we're getting what looks like an upside down U shape. This is called a parabola. And you'll get parabolas anytime you see powers that are raised to the second. And this is also the reason why this is not a linear function, because this graph is not a line. And because the graph is not a line, this is not a linear function. Because the graph is not a line. All right, and moving on. In the next example, we're asked to use the graph. So we're given a graph and we want to use that graph to evaluate each of these expressions. So f of 0, f of 2, f of 4, and f of negative 4. So we're looking for the value of the function for this first example when x is 0. So looking at our graph, we want to know what happens to this graph when x is 0. So when x is 0, we're right here at the origin. What happens to our graph? Our graph crosses the y-axis at negative 2. So the value of this function at f of 0 is going to be negative 2. F of 2, what happens to our graph when we're at 2 on the x-axis? The graph is right here at the origin. So the graph is at 0. The value of this function when x is 2 will be 0. Now the value of the function when x is 4. What happens to our graph when x is 4? Our graph is here at positive 2. So the value of that function at 4 will be 2. And now the value of the function at negative 4, when x is negative 4, our graph is at negative 6. So the value of that function is negative 6. All right. We're asked to use the chart above to answer the question. First, we're finding f of negative 5, and then we want to know if f of x is equal to 23, what would the value of x be? We have two rows. We have a row for the x coordinate. We have a row for the function. Now, when we find the value of the function when x is negative 5, we're going to look at our row with the x coordinates and find negative 5 right here. What is the value of our function when x is negative 5? The value of the function is 96. Now, if we're given the value of the function, so we're looking at the second row, and the value of the function is 23, what is the x coordinate? So let's look and see where we see 23 for f of x. We see it in two locations. Therefore, we could have two possible x coordinates. X could be negative 10 or positive 10. We could simply write plus or minus 10. All right. Now we see a parabola here. We want to assume that this graph extends indefinitely. So that means we could put arrows at the end of this parabola. It's going to continue to grow and grow on both sides. And we want to find the domain. Remember, the domain is our x coordinates, and we want to find the range, that's our y coordinates. We also want to determine if this graph represents a function. Now, when we look at the domain, we want to know what are our potential x coordinates. Now, this graph continues indefinitely. We want to know which values are used or could be a part of this function along the x-axis. We see already that negative 2 is involved, negative 1 on the x-axis, 1, 2 is involved. Even out here, we have 3 and 4 that are involved because this graph continues to move on. The graph could continue to go on indefinitely, right, beyond what we could see. We'll see that the values of the x could increase on both sides. Therefore, x could be any number, and we would write that our domain could be all real numbers. Now, what about the range? This time we're looking at the potential values of the y coordinates. Now we're looking at this parabola. We see a point where our graph shifts right here at -4. We don't see any values represented below -4. Therefore, our range could be any number that's larger than -4. It could be -4 itself, or any number that's larger than -4. So our y coordinate could be any number that is greater than or equal to -4. Does this graph represent a function? To determine if this graph represents a function, we're going to draw vertical lines. We're going to perform a test called the vertical line test. After we draw the vertical lines through the graph, vertical line, a line that goes up and down, we want to draw a couple of lines, and we want to determine if each of those lines will touch the graph only one time. If the vertical line touches the graph once, then we would say that it is a function. If any if any vertical line touches the graph more than one time, then we would say that it is not a function. So looking at our graph, we're going to draw a few vertical lines. So I'm going to draw 1, 2, and a third line. Now, looking at the first line, line 1, how many times does line 1 touch the graph? Right here, 1 time. Line 2 touches the graph 1 time, and then line 3 touches the graph 1 time. Now, because each of these vertical lines touch the graph only once, we would say that this is a function. So yes, this is a function because it passes the vertical line test. Now looking at the next example, we're finding the domain, the range, and we're determining if this is a function. Now looking at our domain, what are our potential x coordinates? Look at the x-axis, and we see the values along the x-axis between -1 and +3. So the way that we represent the values for the domain, we would say x could be between -1, we'll put the smallest number on the left, and +3. And in between those numbers and x, we will place inequality symbols. So x could be numbers that are, it could be -1 itself, or any number that's greater than -1, but it can't be larger than 3. So somewhere in this range, x could be between -1 and +3. Or x could be -1 or +3. That's why we have the equal to symbols. So -1 less than or equal to x, less than or equal to +3. Now looking at the range, let's look at our potential values for the y coordinate. We see that our range extends from 0 to 4. So we will write that our y coordinate could be between 0 and 4, and in between we write our less than symbols. So 0 less than or equal to y, less than or equal to 4. Now, in drawing our vertical lines to perform the vertical line test, we see that each of these lines touch the graph 2 times. Now, because these single lines touch the graph more than 1 time, this is not a function. You would say no, not a function. This does not pass the vertical line test. So it's not a function. Let's move on to the next example. We have another graph here. Our graph is a little bit shorter, and we also see an open circle here. What that represents is a value that does not exist. So it's shaded in right here between 4 and 6. That point would be 5. Here between 2 and 4, that point is not shaded. So the value of this function cannot be 3. The x coordinate could not be here at 3. Also, we want to refer to the y coordinate between 0 and 2. That point will be 1. So to find our domain, what are our possible x coordinates? Look at our graph. It extends between 3 and 5. So our possible x coordinates range from 3 to 5. So x is somewhere between 3 and 5. Now could x, it's somewhere between 3 and 5. Now could x be 3 itself? No, it could not. That's what that open circle represents. So it would just be 3 less than x. Now could x be equal to 5? Yes, because we see the colored in circle. So x could be less than or equal to 5, but it can't be 3. It could be greater than 3, equal to 5, any number that's between this range. We'll represent that as 3 less than x, less than or equal to 5. Now looking at the range, our y coordinate could possibly be, so here our largest value is between 2 and 4, that will be 3. So our largest value is 3. Our smallest value is 1. And again, not equivalent to 1, but between 1 and 3. So less than, and then less than or equal to. So 1 could be less than y or less than or equal to 3. If we were to draw vertical lines through this graph, we see that our vertical lines touch the graph only once. So we would say that this is a function. Yes, this is a function. Now let's look at another graph. We see this horizontal line and we're told that it extends indefinitely. So the line goes on and on horizontally from left to right, and that's going to impact our domain when we look to see what the potential values of our x coordinate. It could be any number because that line continues on forever and ever. We have all values here on the x-axis. We would represent the domain as all real numbers. Now what about our range? Let's look at our possibilities for the y coordinate. Where does this graph intersect? The y-axis is right here at 3, and that's the only point that it intersects. So our range could only be 3. Now let's perform the vertical line test. Look at our vertical lines. They touch the graph one time. Each line touches the graph one time. Therefore, this does represent a function. We would say yes. Yes, this is a function. All right, now let's look at another graph. We want to assume again that this graph extends indefinitely. So when we ask about the range, we're looking for the possibilities of the x coordinate. We see a starting point here between -4 and -6, that'll be -5. And then any value that's greater than -5, because that graph is going to continue to extend. So our range for the domain would be numbers that are greater than or equal to -5. So x could be greater than or equal to -5. Now our range, the possible y coordinates, look, we have 0 in there, and then the graph continues to grow. So it could be any number along the y-axis. We would say all real numbers for the range. So all real numbers, our range. Now, does this graph represent a function? Let's perform the vertical line test. We can see how our vertical lines touch the graph in 2 places. So we would say, no, this is not a function. All right, our next example, we have a column for the domain, a column for the range. Remember, domain represents the x coordinates and range represents the y coordinates. So these arrows show a mapping from A to X. That one arrow represents the ordered pair A, comma, X. From A to Y, that represents the ordered pair A, comma, Y. From B to Y, that represents the ordered pair BY. And then from C to Z, that represents the ordered pair C, comma, Z. What we're looking for to determine if this is a function is different x coordinates. So anytime we have a function, our x coordinates must be different among our ordered pairs. We see immediately that the first and second points have the same x coordinate. They have the same x coordinate. They share a domain. Therefore, this is not a function. So no, not a function, because 2 of our pairs share an x coordinate. So it's not a function. And we can explain that it's not a function because two points share an x coordinate. Now you can test this yourself by plotting these 4 points, connecting them to create the graph, and then performing the vertical line test to see if the graph passes the vertical line test. Now let's look at the next example. This time we're given 3 ordered pairs and we're asked the same question. Does this relationship between these 3 ordered pairs, does this represent a function? So let's look at our x coordinates. We have 3, 1, and 3 again. So a shared coordinate. That means this is not a function. Again, because these 2 ordered pairs share the same x coordinate. So it's not a function. and 2-point shear and x-coordinate. And let's look at the next example. The number of Harley-Davidson motorcycles manufactured in thousands between 1985 and 1995 can be approximated by this formula. We have this function n of x equals 6.49 or 409 in parentheses x minus 1985 plus 30, where x represents the year. We want to evaluate the value of the function when x is 90. So we're going to substitute 1990 here into our function everywhere we see x. And then we want to interpret the result in words. So let's find the value of the function first, n of 1990. And n of 1990 equals 6.409. And in parentheses, we have x minus 1985 or 1990 minus 1985 plus 30. So we want to simplify here. We have in parentheses 1990 minus 1985, that'll give us 5. We have to multiply that 5 and 6.409. You want to multiply these numbers together, and then we want to add 30. Now when we simplify, we should get 62.045. Now what that 62.045 represents, it represents the number of Harley-Davidson motorcycles in thousands. So the 62.05 is in thousands, and when we go to interpret this in words, we want to represent it accurately. So 62.045 thousands, we have to multiply that times 1,000, or move the decimal point 3 places to the right. So how many motorcycles does this represent? In words, we would say that in the year 1990, so in 1990, $62,045 motorcycles were manufactured. They were built, they were made. So 62,045 motorcycles were made. And this is the last example from section 2.1 notes. We'll end here.